You have never actually seen a three-dimensional object. Every solid item around you, your phone, a coffee mug, your own hand, is opaque. Matter on the outside blocks light from bouncing off the inside. When that light hits the back of your eye, it carries zero true depth. Your retina is essentially a biological projection screen. It receives a strictly flat two-dimensional map of light and shadow. The depth you experience every day is a highly convincing trick. Your brain takes that flat map and rapidly processes visual cues like perspective, parallax, and shading to guess the physical object's real shape. Human vision is a mental decoding process of flat projections. The 3D physical world exists, but the visual reality you inhabit is a spatial interpretation you learned to construct when you were an infant. In the early 20th century, a group of painters recognized this biological boundary. Instead of creating another perfect illusion of single-point perspective, they deliberately broke the rules of how space was drawn. Pablo Picasso and Georges Braque developed cubism when the public and academia were captivated by early mathematical theories of a fourth dimension. Their geometric logic was precise. Rather than painting an object from one fixed location, they forced multiple static viewpoints onto a single flat canvas all at once. By doing this, they were mapping an object as it existed across multiple points in space and time. If painters used a static 2D canvas to communicate a four-dimensional concept over a century ago, we can use the dynamic 2D screens in front of us right now to mathematically visualize 4D space. Imagine a completely flat universe. In the 1884 novel Flatland, two-dimensional beings exist entirely on a geometric plane. A flatlander in this world has a visual field limited to exactly one dimension, a line. When this flatlander looks at square, he only sees a single flat edge. Yet, by moving around the shape and using basic math, he learns to infer the two-dimensional area hidden from his view. Now step up to a hypothetical four-dimensional being looking down at our world with true volume vision. This observer could view the heavy steel exterior of a locked safe and the delicate contents inside it simultaneously with a single glance. Because our brains lack true volume vision, trying to picture four-dimensional space organically is impossible. Our only reliable pathway in is to follow the Flatlander strategy, learn the mathematical rules of how higher dimensions project downward. This tesseract is a 4D cube projected onto your 2D screen. Intuition says the smaller cube nests inside the larger. That's a 4D perspective illusion. They are the exact same size, just separated by distance along an invisible fourth spatial dimension, the W-axis. By reframing a difference in size as a distance along a new geometric axis, you stop seeing a shifting, distorted 3D shape. Your brain accurately decodes a rigid four-dimensional object. We can replace the abstract wireframe geometry with something familiar, a Russian matryoshka doll. In 4D space, these dolls aren't hollow nested shells. They are solid objects separated by distance along the fourth dimension. During a mathematical rotation, the furthest doll swings forward along the W-axis, appearing to scale up as it swaps places with the nearest one. Recognizing that scaling effect as a physical rotation recalibrates your visual framework. It proves your mind can consciously process and navigate geometries physically impossible in our world. Up to this point, we have operated entirely in the realm of Euclidean mathematics, a theoretical space where all axes behave exactly the same way. Physical reality operates differently. While four spatial dimensions remain unproven in nature, physics relies on a very real, measurable fourth dimension, time. Albert Einstein replaced independent space and time with a single unified continuum. This diagram outlines Minkowski spacetime. It treats time as a literal geometric axis that intersects the physical dimensions of length, width, and depth. However, time acts under different mathematical rules than physical space. In Minkowski's equations, calculating the distance between two events requires subtracting the time component, introducing a mathematical minus sign into the geometry. Time operates as a structural, geometric axis necessary to map physical reality. Today, physicists use high-energy particle collisions at facilities like the Large Hadron Collider to search for evidence of higher dimensions looped into microscopic physical scales. Over a century ago, the Cubist painters rejected standard perspective, seeking to reconstruct space and time on a flat canvas. Mathematicians discovered that by applying strict rules of geometric perspective, our brains can map an invisible hypercube onto a flat screen. And physicists utilize the fourth dimension to calculate the literal fabric of spacetime. The fourth dimension is a mathematical framework that provides the coordinate system to navigate our universe, accessible to anyone willing to look past the surface of a flat image.